So in a previous video, we looked at some tools for managing normally distributed data. Now we're going to just apply those and try some practice here. So first question is, what percent of EMU students can hold their breath for over a minute? Now I actually have data on this for a couple hundred students. And of those students, the average breath holding time was 47 seconds with a standard deviation of 20. So let's assume that this is a perfect normal distribution, which it probably isn't perfect, but let's see how the calculations would play out. So the mean is 47. Remember, that's Greek mu for mean. And the standard deviation is 20 seconds. That's sigma for standard deviation. Now, what do we do here? Well, we want to know what percentage hold their breath for over a minute. A minute would be 60 seconds. So here this x, sometimes it's the raw score if we want to compare a single person to the entire distribution. And sometimes we can see it as a cutoff. In this case, we're going to see it as a cutoff of 60 seconds. So I'll press that. And notice I already had it selected x greater than. If I would have done this, this would have been the portion that held their breath for less than 1 minute, or the estimated proportion. I'm using the greater than sign, so I get this colored portion. Look at the picture. Let the picture help you. This is what I want. I want to hold their breath over a minute. So this is the side I want. And so we'd say 0.2578, or we could move that decimal place over to decimal point over 2 places, and get 25.8% would be, 25.78%. So what about using a simulation, or how does a site like this even get their data from? Well, it comes from these simulations. So this is Casey's simulation of breath times, and this was done very well. So we have 500 breath times. The formula was used based on a normal distribution. Ooh, and let me check. We have 48 and 21 here. I forgot that maybe the times have increased a little bit. So we had, let's see, 47 and 20 back to match the data. So I'm going to do 47 and 20 and press enter. And then I'm just going to apply this formula to the entire. You can see we're down to 500 and there we go, 500 rows of data and one header. So now we have this simulated data, and if we wanted to figure out what portion of these numbers are over 60, so we have 500 different simulated breath times here, what portion are over 60 seconds, and is this close at all to the answer we just got? Well, let's take a look. So we can do the COUNTIF formula, and we'll count everything in column M. So that's M:M. We'll select everything in column M. And then we're going to do greater than 60. And notice I do put this in quotes. So what this is doing, it's looking all through column M and just counting how many numbers are above 60. And that would give me the total breath times that are above 60. If I want to know what percent of the 500 are above 60, I'm just going to divide that by 500. And you can see here I get 24.8. If I press something again, 23.6, 26.2, 27.4, I'm really hovering around that, that 25% mark. A couple are a little bit lower, a couple are a little bit higher. But those simulations are how these numbers are derived also. They just do a lot more than 500 simulations. Okay, and what about if we reverse the question? So instead of saying what portion of EMU students hold their breath longer than a certain time or less than a certain time, what if we wanted to be in the top 10%? So now instead of having some raw cutoff and then trying to figure out what portion are above or below that cutoff, we know what the cutoff is. We know that we know what percent we want to be in the top. So we want 0.10 here, And we don't want the portion, or we don't want above. Oh yeah, we do. Sorry. So this is the 10% up here. This would be the top 10%. In other words, the people who are holding their breath longest, the top 10% of all EMU students, that would be 72.63 seconds. So if you want to be in the top 10%, you've got to hold your breath for longer than a minute 13, basically. And again, what we did here, since we had the percent, we put it in over here, and that told us how many seconds we needed to get above that. Before, we had put 60 here, we had put the number of seconds here, and that told us what percent was above or below that particular cutoff. Let's take a look at another one here. So this is what we got there, about 72.6 seconds. And by the way, that even though our distribution isn't perfect for EMU breath holding, you can see that the actual answer was 73. And in order to get in the top 10% of the actual people who've held their breath at EMU in my stats classes, it was 73 seconds got you into the top 10%. So this estimate here, based on the normal distribution, was really good, even though the true distribution wasn't quite normal. That shows you some of the power of the normal distribution. Okay, this one's a little trickier. March Madness. I boast here a little bit. The time before COVID, when there was a March Madness before the COVID March Madness came, I won a March Madness bracket, not because I know about basketball. I honestly just knew probability and statistics and used some stuff from 538 which is a prediction site. So the question though is, up until recently, a number 16 seed had never beaten a number 1 seed. So a 16, you get the top 16 teams in each of 4 regions, and the lowest of those 16 always starts off by playing the highest ranked, the 16 seed and the 1 seed. So the 1 seed comes in certainly the favorite in most cases. And up until recently, when UVA got beaten a couple years ago, a number 1 seed had never gotten beat by a 16 seed. And so here's an example from 2019. We have a couple. Duke played North Carolina State. So all of these were the number 1 seeds, and all of the number 1 seeds beat the number 16 seeds back in 2019. So what I'm saying is, let's take a look at how many points the number 1 seeds won by. In other words, when a really good team played the lowest team in the tournament for their region, how much did the number 1 team win by? In this case, 85 minus 62 is 23, so they won by 23 points. Virginia beat Gardner-Webb by 15 points, and so on. So what I did is I plotted all those, how much the number 1 team won by. And I plotted that all in a histogram. You can see that here. And it looks pretty normal, right? Pretty normal distribution. The mean of this distribution is 24.7. So on average, the number 1 seeds beat the number 16 seeds by about 25 points with this standard deviation. So according to this, something that we might be interested in, how often will this upset happen when a 16 seed beats a 1 seed? Well, if you think about it, it's a little bit tricky, but let's go ahead and I'm going to clear this out. So the mean we have is 24.7, and the standard deviation is 12.1. What do we have here? Which type of problem? Well, in order for a number 16 seed to win, it would have to be a negative number, right? The numbers we're plotting are how much does the number 1 seed win by. So if the number 1 seed actually lost, that would be a negative number. We want to know what portion of this normal distribution is below 0, because those negative numbers are when the number 16 seed actually had more points than the number 1 seed. So this is the portion of times when the 1 seed wins. If we go this side, looks like about 2% of the time the number 16 seed should win, should upset. And that's indeed what happened when UVA got upset. Okay, there we go, a few examples.